The 78XX family, like the 7805 and the 7812, is a well-known linear voltage regulator IC in the Hobbyist world. With just a couple capacitors, it is able to provide a regulated voltage at its output. However, the typical output current goes from 1 amp up to 1.5 amp maximum, given sufficient power dissipation. How is it possible to increment the output current? Well, it is necessary to implement an additional power transistor, as visible from this schematic. This is an already well-known circuit. Nevertheless, it seems that there is a lack of a rigorous explanation of the working principle. Today you'll learn how to analyze an apparently simple circuit the engineer way, doing all the math needed so that you can apply these ideas in more complex circuits. Before starting with this analysis, it is necessary to create a model for our regulator so that we can use it for the circuit analysis. Linear regulators, although looking very simple, are fairly complex on the inside. This, for example, is the internal schematic of a 7805. Fortunately, we don't need to understand all of this to create a simple model for our purposes. Let's think about the terminal behavior. Ignoring all the second-order effects, the output simply provides a constant voltage. Therefore, we can think about it as a constant voltage source. But what about the input? If we ignore any power loss, it is possible to think about it as a current-controlled current sink. Whatever output current is required from the load, it will be required from the input terminal as well, still considering a 100% efficiency. But this bold assumption doesn't actually affect the math. And here's our linear regulator model. We can now implement it in the original circuit. We'll call ID the current flowing from the output of the IC, IL the current going to the load, here represented by the resistor RL, and finally IC the current flowing out of the transistor collector. Note that VDD is actually the input voltage Vin. Let's now consider the situation in which the load requires very little current and the PNP transistor is off. Therefore, IC is equal to 0 and the load current will be all provided by the regulator. If the current increases, the voltage drop across RB will increase as well. There will be a current value I tilde where the voltage on RB will be equal to 0.6 volts and the transistor will start to conduct, since you can note that the voltage on RB is equal to the voltage on the emitter-base junction of the transistor. I tilde will be then 0.6 over RB. For example, if RB is 1 ohm, I tilde will be 600 milliamps. That is, the transistor will start to conduct when the output current required by the load is more than 600 milliamps. Now that the transistor is on, we can simplify the analysis by considering its equivalent circuit, where the base emitter junction is represented by a diode and the emitter collector junction by a current-controlled current source, where IC will be equal to the base current IB times the current gain beta F. Considering KCL at the base junction, it is trivial to see how ID is equal to the base current plus IRB, that is, the current coming from RB. Therefore, as VRB is the emitter-base junction voltage VEB divided by RB, the base current can be expressed as follows, where VEB can be approximated as 0.6 volt. Trivially, as the collector current is the base current times beta, we can express IC as visible here. Still from KCL, it is obvious how the load current is equal to the sum of the current coming from the regulator ID and the one coming from the transistor IC. Knowing the expression of IL, simply V0 over RL and the one of IC found before, with some simple algebraic passages we can find the following expression for ID. Now, since beta F over beta F plus 1 is approximately equal to 1, we find this. But 0.6 over RB is the expression of our I tilde. And so, like that, we finally found that the regulator will supply to the load only a current I tilde, plus the second term, which is actually small since beta is usually high, while the power transistor will supply most of the current. We made a lot of simplifications, like assuming a constant voltage drop on the base emitter junction, but the concepts remain valid. Oh, and be aware that this configuration bypasses any short circuit protection of the regulator,